So, now Tuyere shape, dimension and its protrusion inside the furnace are very important parameter to get a good size of raceway and its deeper penetration into the coke bed. So, again we are talking about the raceway and how size and shape can be controlled. So, one of the thing is Tuyere. So, based on the manipulation of the above parameters, one can get the central or peripheral gas flow. Deep penetration of raceway is obtained by lowering Tuyere diameter or increasing the Tuyere protrusion, but that Tuyere protrusion you can increase only to certain extent. So, that again has to be optimized, because too much Tuyere protrusion will be really obstructing the metal flow and burning of the Tuyere will occur very often. So, usually Tuyere protrusion inside the furnace is around 25 centimeter, which also minimizes the burning of the wash line. Some cold model study. Now, I am not sure whether you are understanding this Tuyere protrusion. This figure I will explain you the Tuyere protrusion. So, this is actually the furnace wall. So, this which is this is a Tuyere. So, this is called the Tuyere protrusion. So, the black part which is extending inside the blast furnace is known as the Tuyere protrusion. So, this is very important, and that also affect quite a bit raceway shape and size of the blast furnace. So, this is about the Tuyere protrusion. So, some cold model studies figures are shown below, which highlight the effect of above parameter on the raceway formation and the gas flow. So, these are some cold model studies of the Tuyere in a two dimensional form. So, you have a one Tuyere where the gases is coming and coming out again from a small slit, but you have restricted in this way. So, you raceway is getting quite a lot support from this wall over here. In another one you are having from the central opening is still probably a bit low in this one, but this is all solid materials. So, again the raceway is getting a support from this material. Another one again is a central injection is coming, but the Tuyere is very thin actually in this case. So, raceway which is formed in front of it does not get any support from the Tuyere, which is usually the case in the blast furnace, because blast furnace Tuyere does not give a support to the raceway, especially the Tuyere wall. So, this also is indicated in this figure. So, as the blast velocity increases, you can see the raceway penetration is increasing, but in the case of this Tuyere you can see it is not giving such a good result, and it's you need a very high blast velocity even to form the raceway. Same case in this one, you need a quite high velocity to form the raceway, then it keeps quite okay, but you still get a good support from the Tuyere wall. In actual case this is not the thing, and if you look at the third one, this start giving you the raceway even at a lower velocity and keep on giving a good penetration of the raceway without supporting the raceway by its wall. So, these Tuyere people have found is quite good in doing the experiment, and that is also true in the actual blast furnace. So, that shows how the Tuyere even size or support can change the raceway penetration. So, another important parameter is the spacing between two tuyers, as considerable amount of slag and iron flows through intertuyer zone. You will understand this in the next slide. Therefore, proper heating of metal and slag is necessary which is passing through this zone. Otherwise, inadequate heating will affect the thermal state of the hearth with high sulfur content in iron, sluggish slag movement, erratic metal analysis, etc. So, okay, I think before this let me show you this, so you can understand a bit about the interspacing what we are talking. So, this figure shows the Tuyere arrangement in a typical Japanese blast furnace, Kokura 2 blast furnace. So, it is about 22 tuyers across the periphery in all cross sectional area, which are having of course quite different opening. If you look at, it is varying, let us say here the 70 millimeter, and then 140, 130, 120. So, total there are 22 tuyer, and some of them also do not operate, or you can switch any of them, in fact you can switch them off or on. So, as you will see, this is the raceway from this tuyer, this is another raceway from this tuyer. Now, the liquid is flowing around it, and it is flowing through this, and so same way from this raceway it is also flowing in between. So, this is the one which we are talking in the previous slide, that liquid and slag is flowing between the interspacing of the tuyer. So, this is the interspacing of the two tuyer, and certainly if this is high interspacing, then heat penetration in here would be low, and that is where you have to have a minimum at least interspacing so that the liquid metal or iron should not get solidified or affect adversely this space. Otherwise, if it gets solidified, it becomes more viscous, then you are having a more problem with respect to permeability and flowing of the gases and the liquid. So, this interspacing between the liquid is very important, and this is what it says: flows through the intertuyer zone, and proper heating of metal and slag is necessary which is passing through the zone. Otherwise, inadequate heating will affect the thermal state of the hearth with high sulfur content in iron, sluggish slag movement, erratic metal analysis. So, therefore, intertuyer spacing should be like that, their combustion zone should be at the verge of merging, forming a continuous peripheral ring. Usually, intertuyer spacing is about 1.5 meter. For large blast furnace, it is given like a number of tuyers is equal to the 2 multiplied by the hearth diameter plus 1. For modern blast furnace, it is a 3 multiplied by hearth diameter minus 1 or 2. This is again sort of a rough idea which says okay, this sort of interspacing should be there between the two tuyers. So, it says spacing is about 1.5 meter. So, if you look at this, if this is 1.5 meter, and in large one usually if you are having a 1.5 to 2 meter raceway size, So, so what you are having about 0.75, 0.75. So, these are almost merging over here. So, zone is very hot. So, the adequate heat would be there. So, liquid iron and slag will not freeze and earth will not get cold. Sulfur content will not increase. So, you need, and that is why this what type of flow around the Tuyere we call like a peripheral ring. In fact, this ring in fact we say peripheral ring through which the gas flow or reducing gases are coming out. So, almost all of the region here the gases are coming out. So, they are sort of raceway sort of they are merging to each other in this. So, beside that now there is a one phenomena called the raceway hysteresis. So, it is observed that all the experimental correlation have been based on various form of Froude number. Even if you look at the previous one which we said, this is also sort of a Froude number V square G L. So, that is a Froude number. So, most of this thing has been based on the Froude number, V is the velocity, acceleration and the characteristic length. So, the raceway size has been intuitively correlated with this number along with some other parameters such as height of the bed, width of the model and Tuyere opening. So, most of this study have been done in the cold condition at room temperature at laboratory scale. So, most of the empirical correlation for 2 and 3 dimensional model have been obtained for the velocity increasing case. It must be mentioned that one can get 2 raceway size at the same gas velocity depending on whether measurement is made in the increasing or decreasing gas velocity. This phenomena is called the raceway hysteresis. You will understand from the actually next slide about the hysteresis. So, you know as the gas velocity increase, the raceway size or the cavity will increase. So, if you plot this with respect to the blast velocity, you will find the and this is the raceway equivalent diameter, the raceway size is continuously increasing as you increase the velocity, and at certain velocity you hold it and you start now you hold it at that velocity, you start now decreasing. So, when you start decreasing the velocity, what you find, the size of the raceway which you are getting almost 9.5, it is not reducing much, it is almost constant up to a certain velocity, and after that velocity it start decreasing more as a linearly. So, does not matter you and again you stop somewhere, you start again, it is going to follow when you start increasing, but when you start decreasing the velocity is follow the linear path, and when you are increasing it is following a non-linear path. So, if you take a typical velocity let us say 50 meter per second, what do you get? You are getting about 2 centimeter raceway when you are increasing the velocity, and it also crosses this which is about 5 centimeter plus. So, really what you are having, you are getting a 2 raceway size at one velocity. So, one is in the decreasing case and one is in the increasing case, and that so this typical phenomena is known as the hysteresis. As you can see, is a hysteresis sort of curve, and that is the one which is discussed about the hysteresis that has been formed, and 2 raceway size at the same gas velocity one is finding. And most of the experiment usually is done in the increasing case. As you can see now, we talked about the Froude number. So, this Froude number is changing with various sort of exponent. So, and all these exponents are changing by various investigators. So, they are not constant. So, certainly something is wrong if you compare your Raceway size with one correlation, then the other correlation does not give you the same Raceway size. So, dr is the Raceway diameter, these are standard parameter, gauge density, blast velocity, Tuyere diameter, solid density, acceleration due to gravity, void fraction, and this is the bed height of particle diameter. So, the same thing, but each of these correlation are different and they give totally different Raceway diameter. So, they do not really talk to each other in one way. So, certainly there is a problem, and that problem actually is because they were doing the experiment, probably one is mostly in the increasing case and could be in between also, but never the less they were not doing in this decreasing condition. So, it has been reported that decreasing velocity correlation is more relevant to the blast furnace, since the Raceway size in the increasing and decreasing velocity case vary by approximately factor of 3, the Raceway size can affect considerably the prediction of heat mass and momentum transfer in the blast furnace. So, when we say Raceway size is more relevant, decreasing velocity correlation are more relevant to the blast furnace, the reason is in the blast furnace because the coke is getting consumed here in the Raceway. So, the whole burden is descending down, and in the decreasing one, when you go to a maximum value of the Raceway and you start decreasing the gas velocity, again the burden at the top of it is start moving down because the Raceway size is decreasing. So, that corresponds almost the same condition as in the blast furnace when the solid is moving down, and that is the reason this statement is made that decreasing velocity correlation is more relevant to the blast furnace, and this has been found true and it has been shown, and that is where was the problem. So, therefore, the final form of the correlation for increasing velocity is given. So, in this, and you can see it is a sort of a non-linear Froude number, it still is there, but it is giving a little bit non-linear behavior in the increasing velocity case, and it includes also the friction coefficient, the frictional properties of the material, which is very important, and Raceway is quite dependent on that. Same parameter rho effective it is defined in this form: void fraction, gas density and particle density, and d effective is particle diameter and shape factor, and decreasing condition it is defined in this, and which you can see is more or less linear 0.6 only, and that is with the your Fourier number. So, that is how it gives the linear profile in the decreasing case, but again this friction coefficient is there. So, frictional effects are dominating, and this shows the validity of this correlation. So, this is the Raceway diameter and this is the Tuyere diameter. So, there is a comparison of this. So, one with the blast furnace, the Japanese blast furnace. So, these are the actual data of the operating blast furnace of the Raceway, and these are the prediction made by the decreasing correlation, and these are the prediction made by the increasing correlation. So, obviously decreasing correlation gives and satisfies and reasonably can predict the Raceway size in the operating blast furnaces. So, now we have some sort of robust correlation for Raceway diameter to predict in the operating blast furnace. So, there is one problem based on this. The lower part of the blast furnace is simulated at laboratory scale cold model, where spherical plastic bead represent the Koch matrix. Air is introduced laterally at a velocity of 15 meter per second. Other parameters are given below. So, particle density, it is 1080 kg per meter cube, your gas density 1.17 kg per meter cube, the particle diameter is 2.1 millimeter, void fraction 0.42, particle wall fraction is 0.22, wade height 600 millimeter, Tuyere opening 5.5 millimeter, wade width is about 380 millimeter. And as we know, the rho effective is given by this and D effective is given by this. So, calculate the Raceway diameter for both increasing and decreasing gas flow rate using the correlations which were discussed before. So, the effective density of the charge would be substituting the value as given in the example, gives you about 627 kg per meter cube. And because the spherical plastic beads are used, and so step factor we take 1. So, that gives you the effective diameter 2.1 into 10 to the power minus 3 millimeter. And Raceway diameter for the increasing gas flow rate, we know it can be given by this correlation, and it is the question of substituting the appropriate values which all are given, the gas density, blast velocity, Tuyere opening, even the effective density we calculated, effective diameter we calculated, gravitational constant, height and width, and the friction coefficient. So, by substituting these parameter into this correlation, essentially what we get, dr equal to 11.6 millimeter, and actual really diameter is about 11. So, very close match, but that is for the increasing case. If the same thing we can do for the decreasing gas flow rate. So, under the decreasing velocity correlation, of course, you have different indices. So, again you can substitute these value, appropriate one which are given in the example, and one can calculate then the Raceway diameter about 28 millimeter, and actual diameter is 28.5, again a very close match. So, this correlation gives a very good predictions about the Raceway diameter, whether it is in the cold condition or it is in the actual blast furnace condition which we had seen here. So, at least for the blast furnace size, we have some sort of the correlation which can predict reasonably well and the size of the. Now, the next one is about the moving bed. As you know, in the blast furnace the burden is continuously moving downward, and we have talked all about this since we started this course. So, essentially what is happening, in front of the Tuyere, coke is getting consumed. When the coke is getting consumed, then the void is formed and it has to be replaced by the surrounding solid. So, mostly from the top, then coke comes down and replace that coke which got consumed in the raceway. So, the whole burden start descending down. This is not just only this one, even the your slag and liquid is forming in this region, which also reduces the porosity. So, the whole burden is coming down, but most of the coke consumption is occurring and coke is replenished from the top. If you remember in one of the slide, I have mentioned that a funnel type flow exists above the raceway. So, because raceway shape is more toward the upward side than horizontal side, and so coke is coming in this raceway region from the top. So, this is like a funnel type of flow. Very little coke comes from the side, and so most of the coke flow is occurring from the top, which is like a funnel type of flow coming into this region. And here the coke movement is almost nil or very little, and that is the reason this region is known as middle one, the dead man zone. Almost there is no coke movement here, or very little. So, so essentially, if you look at in one way, the whole burden is descending down up to here. So, this is not any stationary bed, it is a moving bed, and that is where actually one has to look at whatever experiment and things are being done, it has to be done under moving bed condition. So, coke flowing into the raceway, sluggish flow into raceway at lower part of deposit, sluggish descent, periodic heaving motion. So, this periodic heaving motion, when you are taking or draining out the liquid, whether it is iron or slag, that time the whole this dead man zone it comes down, which is floating on this. So, that is how the heaving, periodic heaving motion, and as when you close the tapping hole, it start building. So, due to buoyancy it goes up, and that. So, moving bed has a very different some different properties, not very different. So, this is a larger view of the funnel flow. So, this is the raceway boundary, and the chart line you can see mostly the flow what is observed in a hot metal experiment, that in a very narrow part or near the raceway the flow of the coke and lime is occurring, and away from the raceway boundary in horizontal direction is a dead man zone, and that coke does not participate into the combustion of the things. So, essentially this part is sort of a moving part, and movement of the charge is taking place, mostly the coke in this region, because other thing is in the molten stage. And this figure shows that the void fraction which varies, because the permeability is very important thing in the blast furnace for the smooth operation and good productivity. So, for a fixed bed the void fraction is about 0.5, and for moving bed the void fraction is around 0.6 or 0.62, So, you can see in the moving bed the void fraction is quite high than the fixed bed, and one way this is a good thing for the permeability. So, one cannot take the void fraction of fixed bed for solving the problem in the moving bed. So, one has to be very careful, and of course, this if you look at this with the diameter of the particles, it does not change much. Of course, with the shape factor the void fraction gets affected a bit, but with the size of the particle it does not change much, but certainly the moving bed is giving a higher voids than the fixed bed. And as we were talking also about the experiment in stationary bed and the moving bed, and we saw this this figure we came across where in increasing case it follows this path, and while we decrease the velocity it follows this path. And the experiment which were done in case of moving bed, what it is found that it does not matter whether you measure the raceway size under increasing case or decreasing case, the same size you get it in both. In both the condition if the bed is moving. So, moving, and one more thing it is saying. So, this moving bed raceway size correspond to the decreasing bed raceway size of stationary one. So, the thing which was said that decreasing velocity correlation are relevant to the blast furnace raceway is quite accurate, quite correct, because the moving bed and the decreasing one they are coinciding. So, they give the same raceway, and that is where this decreasing size correlation are fitting well with the actual blast furnace and giving the right predicting the right raceway. So, it is a very important finding that decreasing and moving bed gives the same raceway diameter.